that people were aware of. That was back in October, 14th through the 16th. Within those 2 days, it was really, really nice weather. It was sunny. It was really beautiful. And the government and the TV station talked about the hyperactivity from all the spiders, with the Indian summer activity. And so I walked into these things that felt different than anything else that I've ever seen. Nothing spider web like. And then we got different talks going on in our Telegram channel and stuff. People contacted us and they asked, "Hey, what's this? And have you heard about it?" And says, "Guys, go ahead and start accumulating all these things and send it in so we can look at it." And while this has all happened, we started talking. And maybe first here, I started talking to Philip Zeller. He's a physicist here, very, very well known here in Switzerland. He does presentations all over Switzerland about geoengineering, weather manipulation. So Philip Zeller will be part of this today, and he will talk specifically also about patents and how we got about that. So maybe while we talk about patents here, Philip Zeller actually was the first one I talked to about when we looked at these things. And he gave me a heads up and said, well, if we have a chance looking at these things and we validate that have a whole space inside them, then I have a few patents that validate that this technology exists. So he got me really, really excited, of course, to see, okay, what can we do? And then, of course, I talked to Hans-Jörg Grete, that's also with us here. He's a very well experienced, engineer, and specifically in application. You can talk about then, Hans-Jörg, yourself about all your history and stuff and backgrounds, but extremely well experienced professional in regards to the lab analysis. And so he helped us establish a lab team in the background. So we're here, us three are like the project management team, but behind us is a lab team that will help facilitate this. And so it took us a long time. It took about 22 months from the day we start getting those strings picked up from different places across Europe to where we, in the late fall, this past year in 2024, were able to actually disclose our lab analysis. And so since then, we have different activities happening, and we're preparing ourselves for the next phase. And Hans-Jörg and his team finished some additional methods, and he's going to talk all about it. So this is a little bit, what's happened in the background where we stand today. And so obviously we are extremely excited not to, just to keep it for Europe, but we learned through you that you also have evidence that you also have those mysterious strings, spider webs, they call them, in the United States. So I think we would all greatly benefit by cooperating, communicating with each other. And since we're the first organization worldwide that we're aware of that has done these lab analysis, we have done those methods, and Hans-Jörg will expand on this, that literally anyone that has access to a lab, any nation, anyone could actually validate this themselves. And we're here to help them with what methods that have been used and applied. And with that, I don't want to be any longer. Back to you, Renette.
Well, thank you for that, Christian. Certainly, you and I have been discussing that around the same time these mysterious, weird, fibrous cobwebs came out of the sky. When you pick them up, which a lot of people have collected here in California, around the US, they're not of a natural substance. They just aren't. They do feel like there's some kind of a man-made fabrication. So this is what grabbed many of our attention. We have collected them. I told you around the same time this was happening in Europe. It was happening here. And the fact that we now know that these things can actually carry, they're a vessel, a carrier essentially, for God only knows what. This is really sounding the alarm. So with that, I'll let you take it from there.
Well, that's good. I think I'm going to just go dive in if you're ready to go, and all your viewers. We have a PowerPoint. We're going to go to that, and we'll see how we can go right in there. So anybody can see this here on my screen?
Yes.
Okay, that's great. I'm going to just change a few things here. Great. If I maybe can just go to the full screen, huh?
Yeah, please do.
Oh, this is good. Like that. You can still see everything, right?
Yes.
Right. Great. That was here. What we're going to share with you is the actual PowerPoint presentation, the way we did this with a webinar that was coordinated together with a live stream. We only had 500 seats webinar. And the funny thing was, in 1.5 days, it was completely booked, the webinar. So we had a TV station, Bittel TV here in Switzerland, in Germany, that jumped in and helped us with a live stream. So we were able to live stream this, and there was way over 3,000 people that live followed this. So this is first slide. I talked about Philip Zeller. He's a physicist, the ETH Zurich, which is the equivalent to the MIT in the United States. He will talk to us specifically about the patents and why what we have found out could give us some really good ideas of where this is actually leading, where it's coming from, and who is behind it. And here, as I said, Hans-Jörg Greter, diplomated engineer, application chemist. He's going to give us the main part of this presentation here today, together with his lab analysis. And then from here, I'm going to show you the first time a few of those strings, okay? It has really nothing to do with a spider web. So it's extremely sticky, but the people may have some of those. And I tell you what, after this presentation, I don't think that people will touch this bare hand. We tell anybody, if you collect those mysterious strings, to absolutely wear plastic gloves. They're extremely toxic, we have learned, and you guys will all find out this evidence. Now here, I'm showing you and the viewers a few of those samples and how they came into our nonprofit organization. You can imagine back in the October, November in 2022, everybody was still in the middle of this pandemic and they were all in panic about, are we going to die, everybody? And we were focusing on strings. So here you can see some of those, collected strings and how they showed up in our office. And from here, they went then on to Hans-Jörg and to his lab team. Now here, I'm going to show you a video from strings. I don't think you can actually hear the sound. But this is now from Germany. This is from our friend Mark from Germany, and he's done an excellent way in catching those things. Whoops, I'm going to go one back. You cannot hear, right?
No, well, that's a large one. That's a large one.
Yeah, you can see that this has nothing to do with normal spider webs, okay?
No. Yeah.
You're going to go to the next one. They're about 3-4 meters off the ground. They're like 15 to 20 yards long. And the people going to follow this presentation here, Renette, will be absolutely shocked what capacity and capability those strings actually have. This is enormous.
I've never seen any that long.
Yeah. It's extraordinary. So I'm going to have one more phone clip. Sure. In the very end of this, you can see when he takes in his hand in how different this is and looks compared to a spider web. Check this out here. This is an excellent view. Yeah.
That's not a spider web.
No.
No. Look at that. That's exactly what we've seen here in the United States as well.
Yeah. It's great for us to hear that we're dealing pretty much with the same technology. I'm sure it is. But till we look at it together, we don't know, right?
Correct.
So maybe the most important thing that I would like to share here is that this is now our nonprofits organization's direction where we're going while we're still working in the lab and doing further methods and stuff like that. This is very, very important for you and your team. And if we work with Kennedy and the Trump administration together, this here is the start. This talks about the convention. This is from a UN convention, okay, on the prohibition of military or any other hostile use of environmental modification techniques. So this goes back to 1976 in the UN. And Switzerland, our Swiss government, signed off on this in 1988. Why is this so critical? In this, here under Article 3, they talk about this convention does not preclude the use of environmental modification techniques for peaceful purposes and does not affect the generally recognized principles and applicable rules of international law concerning such use. So what they're saying here is they are allowing for geoengineering, weather manipulation over Switzerland, not specifically Switzerland because we're a Swiss nonprofit, right? But this is for any other nation as well that's part of this. So they're saying as long as we are using it for friendly purposes, we can do it. Well, guess what, Renette? Since the last 2 months, since we came out with this laboratory analysis, we have now evidence in our hands that they're no longer doing it to friendly purposes, okay? Now we actually have evidence to go to the Swiss government and say, hey, we have a problem here. We need your help and we need your assistance. And if they don't do it, then we're going to absolutely go on with criminal charges and start from the bottom up. So this here is a very, very key piece, Renette, that we need to coordinate with the United States. And if, Trump, Kennedy are motivated to help us here, if we can go and expose this worldwide, we have a chance.
That's right.
So here, I'm going to give Hans-Jörg the chance to go in to his laboratory analysis here. Hans-Jörg, I'll let you go ahead.
Okay. So the first slide, it takes a chance to explain a little bit what technique we have used. It proves that we are, let's say, state-of-the-art technologies, and the results I believe, can really prove that with these techniques we have got the most information that is necessary to understand what is happening with these threats. I start with Fourier transformation infrared spectroscopy. That's a spectroscopic technique coupled with ATR. That means attenuated total reflections, where everything can be measured. And we put also the threats on our measuring instrument, as well as solvent extraction. The next type of analysis we use is elemental analysis, is a high-tech instrumentation, which is called inductively coupled plasma mass spectrometry. They are used for both for the material as it is and for the extraction types. Then we had optical microscopy. That is a light microscope, which is well known, I think, to everybody. But additionally, we use the microtome section cuts of the thread embeddings. That is a microtome instrument, a device where you can cut slices for any investigation with microscopes, any type, light, optical, or even with a scanning electron microscope. And this one we used as well. And we coupled it extensively with an energy dispersed X-ray spectrometer. That means we got also information about the elemental composition of that what we put in the instrument. Then again, the microtome section that we used, especially the SEM with thread embeddings. Then one of the techniques which is well known in polymer characterization is pyrolysis coupled to gas chromatography, and again coupled with mass spectrometry. So to get the information, what is pyrolyzed and which comes out as adducts or starting materials, because you have a mass spectrometer in the background where you can identify what is a type of polymer or what is a fragment of a polymer. And finally, the gas chromatography, mass spectrometry coupling with the solvent extraction of the thread material. Next slide, please.
Right.
Then at the beginning, a short summary of the investigations we did of these mysterious fibers or threads. We clearly know by FTIR and pyrolysis GCMS that this material, the threads, the fibers, are based on natural polyamides and not on any synthetic technical polyamides. We believe they are started with amino acids. Maybe they did some derivatives or some modification of the basic amino acids, and they did never use synthetic polyamides like PI6 or PI66. These products are as well known as nylon 6 or nylon 66. There exists quite a big number of synthetic polyamides. I will come back later when we compare it. Then naturally the elemental analysis clearly delivered carbon, hydrogen and nitrogen, which is typical for imates. And maybe the sulfur content we found is a part of any of these used amino acids. Maybe it's cysteine, or it comes from a modification of the polymer backbone. Then metals were detected only in traces, but exception is we have a slightly elevated aluminum value. Then we could clearly prove that scanning electron microscope, that fibers are inside whole. They have a diameter external about 4 to 6 micrometers, or in nanometers 4,000 to 6,000, and the inner diameter is approximately 1 to maximum 3 micrometers. And we clearly saw already with the microscope, the light microscope, and later on with the SEM images, that in the nanoscale cavities there must be material inside included. We believed it was chemical substances. And then later on, we did solvent extraction. It's logical. If you have some material in the fibers, you try to extract it. And we got really good information by IR and GCMS. And we detect roughly more than nearly 50, but I focused on 30, which are really proved by the mass spectrum that these substances could be inside. And these substances are crucial in terms of their saturated, unsaturated, cyclic, even aromatic compounds, ketones, acrylamides, epoxides, histamine, and really quite a lot of a bunch of chemical substances I never heard before all together. And what is interesting and what is really astonishing is that if you look deeper into these substances by the so-called safety data sheets, you will find a lot of GHS. It means globally harmonized systems of classification and labeling of chemicals. And these labelings, these pictograms are really horrible, because we saw things like, we go now to the next slide, please. We saw things which were really astonishing. If you focus only on the red rhombus, you see there's the death head. That means it's highly toxic. Then we have corrosive, maybe it's attacks in terms of irritation of the skin, or even any product, any surface, maybe organic or inorganic. Then we have such which are really harmful to health, includes that it may cause cancer, or make damaged genetic material, or even fertility or anything else. Then the next one is that this may be highly flammable or even explosive.
Yeah.
Next slide.
May I ask quickly, is this
Yeah.
the substance you found inside of the hollow portion, or is this the actual fibrous material itself that
No,
you were?
that's what is inside. That's what was inside the cavity. That is the loading of the cavities.
So make it very clear to people, these synthetic webs are essentially delivering devices. They deliver these
Exactly.
chemicals, these
Yeah.
toxic compounds. Okay.
Yeah, Philip, would you like to expand maybe right there, because that's going to come right back to the patents when you explain the patents.
Well, yes. When we first got these samples, we did, before we started the real scientific analysis, we did some quick and dirty tests, like like burning tests and comparison to real spider web strings. Also diluted them in different liquids, and we saw that they totally behave differently from spider webs. And then when I came up with a huge collection of patents that I have gathered over the years, I told Christian that I have seen such techniques, maybe not in this huge scale as we have observed it on that specific weekend in October 22, that really such substances can be used as payloads within such hollow fibers and can be used specifically for agricultural applications or whatnot. I would say I will come to certain details when we are at the patent slides.
Yeah.
But that's really when we kind of woke up and said that could be more than just an accident. It could be something deliberate. Maybe it was that's speculation, but maybe it was a test use just to see how far it can be spread in a one-off action. So we don't know these details, of course, because we don't know any whistleblower of such a thing. But it was quite obvious to us that there was something going on.
And so one of the things I want to make clear to you, what you're saying as well, is that this material, this spider fibrous material, dissolves in liquid, whether that be rainwater, right, waterways. If you inhale
blood, saliva,
your mucus, it dissolves when exposed to moisture.
Even the hollow fibers themselves, they dissolve, and that's even described in one of the patents. They dissolve, but over a longer period of time. So it takes time for them to dissolve to really have enough time to spread the payload to wherever it's meant to be.
Okay, thank you.
Back to Hans here.
Yeah, just one comment on it. I think that the extraction, what we did mainly with organic solvents, delivered really the content, or let's say what is in the cavity filled in. Because if you solubilize the whole system, it means fibers plus the substances which are loaded inside, then maybe you will get a different picture. But we focused on what is inside. That's why we used as extraction mostly organic solvents. Okay, back to the techniques we used. As mentioned at the beginning, FTIR spectrum measuring techniques. Left-hand side, there's a short scheme about what the instrument, or every FTIR instrument, looks like. You have a source where light is sent via mirrors through the sample cell and goes finally to the detector. And the important thing is that every substance, every sample has a unique IR spectrum, and that's what we call it, a typical fingerprint. The instrument we used is the black one in the middle. In the background, you see the FTIR spectrometer. In the front is the ATR module, which allows us, and then go right side, you see it, which allows us that the IR beam penetrates with a certain depth, depending on the crystal, into your sample, in that case into threads, and we'll get the spectrum. And the technique is the Fourier transformation. Just one marker. Fourier transformation is used to get, it's a mathematical process to get quasi raw data in a spectrum transferred. Next slide. Yeah, well, that's the first spectrum I took with the FTIR. It's a sample or a thread or fiber called 347. It's the first one I got from Christian. And what you see at this for a spectroscopist, it's clear. If you look at the two major bands, around 1600 and about 1500, that indicates clearly that must be amide or polyamide. There's no doubt about this, but it's a unique identification profile which allows a determination that must be that, nothing else.
Next so what you're basically, this is showing us is that it's man-made. It is not of nature. Is that correct?
That is not, at that moment, we don't know it. We simply know it is a polyamide, which has to consist or could consist as from adducts, like they are using in the synthetic processing of polyamides, or it could be something else.
Okay.
At that stage, we didn't not know. Only one thing we know. We saw that there are at these two major bands, there are a fine structure with mostly 4 peaks. And that indicates already, okay, there must be 4 different amides in this polymer backbone. Next slide. Here I compared the typical technical polyamides with that what we found. Focus on the red line. Red line is our thread, our mysterious threads, and all the other colors are technical polyamides which are available on the market, commercially used and applied to different things. And you see polyamide 6 or nylon 6,6, polyamide 12, 12,6, nylon 6,12, nylon or polyamide 11 gave different spectra. Next slide. This is the region. I spread it again. And what you can see if you focus on the red line, the first peak is called, this is a nomenclature which is used in spectroscopy, amide 1, and the second one is called amide 2. That's typical for these substances, and none of the reference substances we had in databases we can measure themselves had any congruence with our sample.
Okay, so now can you, those past 3 slides, break that down in layman terms? Exactly what is it that we're seeing? This is the threads, and or is this also consist of the material inside of it, the payload? And what exactly is it breaking down?
First of all, what we mainly see are the fibers. So it's outer part, because inner part is not easily to detect by this technique. Okay.
Got you. Okay.
Next slide. Okay, then what we did as next is I compared it with the databases. We have several 100,000 data available in IR spectroscopy, and what we can see in this type is the hit. The hit is not a polyamide. The hit is chymotrypsin, and chymotrypsin consists of quite a lot of amino acids, I think over 240 amino acids. So the data match is very close to anything what contains polyamides based on amino acids and not on synthetic material.
And can you give me a definition of what a polyamide is? What is that definition exactly? What is that?
Chemically wise, you have for polyamides always adducts. We come later back once again, but I mentioned it already now. We have adducts like caprolactam. And if you polymerize caprolactam, that's a monomer, then you will get a polymer which is called polyamide 6 or nylon 6.
Okay.
Because it's only made of that. If you have another one, 6.6 or 6.6, then you have 2 adducts in your polymer which are used to make the polymer. One is hexamethylene diamine and the other is adipenic acid. And if you have 12, you have 12, a ring with 12 lactam, which opens during polymerization and gives a polymer which is called polyamide 11 or nylon 11. Okay?
Okay. Got it. Thank you so much.
Next slide, please. This is the region, the FDIR region expanded, and you can now see, keep in mind what we have seen before, all the technical polyamides did not fit with our spectrum of the threads. What you here see now, most of the peaks, I can say nearly all peaks, are identical to our product. And this is another, let's say, proof that the material consists never of a technical polymer. You can also exclude any other polymers like polyethylene, polypropylene, PET, anything what you want. It's focused on polyamide, nothing else. And now we know this polyamide must be made of amino acids because all hits, and the next one, please. Next slide, please.
That was.
Okay, sorry. No,
Can I ask one of the clarifying questions?
Yeah.
What is the significance of amino acids? What's the significance of amino acids as being made of amino acids? What does that mean to you and your team?
Amino acids are absolutely necessary for every human being. Your food consists of meat, consists of amino acids. Your body consists of amino acids. Without amino acids, we could not live. And there are essential amino acids which are absolutely necessary. The body could not produce themselves. You must eat it. And the other ones, you can take it, but if you make bodybuilding, you need amino acids, proteins. At the end, it's proteins.
Okay. Thank you.
And this one here, the thread is again the blue line this type, and we have another hit, the spun silk. And the spun silk or spider silk or chape silk consists mainly of 3 to 4 amino acids. So we have now by interpretation and by the database research a clear proof that this must be a polymer based on amino acids. Okay? Next slide. So that is another overview of all the different threads we got for analysis. You see there are 6 or 7 different collecting places, and I put them all together, and you can see, next slide, we see it better. You can see it, all these are identical. What they have compared with first red, it's the red line, we have all the various fine structure, the fine structure of the major bands, which is called amide 1 and amide 2. Maybe a little bit exception is the sample from Winningen. Maybe I didn't have enough material, or it's maybe too thin on the measuring device, so that the peak intensity is not the same compared to the other ones. But what you can see, look, the fine structure. We have all these single peaks around 1600 and all the single peaks around 1500. That means these threads which were distributed over Switzerland have the same chemical background. Okay.
In other words, Renette, from Italy, Austria, Netherlands, Germany, it's the same stuff. From all these different, places we got all these accumulated from.
Okay, next slide. We're coming to elemental or element analysis. Sorry. Here we use the ICP-MS. You see the instrument which stands in one of my former labs. The major tool of an inductively coupled plasma mass spectrometer is the so-called ICP torch. This is where you can atomize your solubilized, your dissolved sample, and you crack it down in atoms or in polyatomic ions which were detected. And you use again the MS detector, and this MS detector can clearly distinguish between, let's say, that atom or this polyatomic ion has a mass of 46 or 45 or 44. So by this way, we can clearly say, okay, if we have a mass, let's say, about 12, it must be carbon. If we have a mass of 16, it must be oxygen. If we have a mass of 14, we have nitrogen. If we have a mass of, let's say, 35, we have chlorine. If we have any number has a clear designation what it is on an atomic or on an elemental basis.
So what you found here, though, is the 44, 45, and 46, correct?
That's only an example how it works.
Gotcha.
We
Okay.
found completely different masses or different atoms. Next slide, please.
Gotcha.
That's now the result of the elemental analysis with ICP-MS. You see on the left side, we have carbon, hydrogen, nitrogen, which we expect to see with a polyamide. That must be always there. We have additionally sulfur. It's our estimate. Maybe there's a modification, or they used cysteine as an amino acid as a starting material. If you look in the middle, you see all these elements, mainly metals, aluminum, which was slightly elevated, but you also see we have some nickel, we have sodium, we have iron, we have copper, but aluminum is the most, let's say, dangerous element for our brain.
This is very reflective. These elements you found are very reflective in our rainwater samples as well here in the United States.
Yeah, that's it. And then at the rectangle just on the right corner down, we checked the complete periodic system, and all these other elements were below 5 ppm. So we can focus on that, what we found, and these other two rectangles, that's the main part. Okay, next. What we have also used is an optical or light microscope. Left-hand side is the instrument we applied. In the middle, there's shortly how microscopy functions. You see, with a lens, you get the magnification, and the magnification, depending on the instrument composition, you can see small things, particles up to a certain diameter or length. And with the scanning electron microscope, which I show you later, we have another magnification, another dimension. Optical microscopy is limited at a certain magnification, whereas scanning electron microscope, depending on the type of instrument, is expanded till nearly nanometer or even angstrom regions. And what we also use, very important to get these cross sections of the fibers, is the rotary microscope device, a microtomy device, because it allows us, after we have embedded with a material like epoxy resin, like paraffins, like other things, when we have embedded the fibers, we cut it as long as we got the first cross sections where we can see, voila, there is really a hole inside. Next slide.
So this allowed you essentially to cut it without squeezing it together, without crushing it, correct?
Exactly.
So
Exactly.
It's
That's
hollow
the point.
structure.
Yeah.
Okay.
Embedding allows you to keep the embedded material in its original format. Okay.
Yeah.
That is a picture we took from the optical microscope, and this was also the first trials to cut them. We did not have great success because the material at the cutting, especially the cutting method, the cutting knife was not in the right manner. We used for the first trials, we used a steel cutter, a steel knife, and even they are very sharp. We did not succeed in getting clear cuts. But anyway, what you can see on this already is that the fibers which arrows must be hollow. You see it?
Sure do. So
Yeah.
that's essentially where the payload goes. That is how they
Yeah.
deliver whatever
Yeah.
these compounds are.
And the next slide, the picture on the right side clearly proves.
Oh, sorry.
Really proves you see a hollow fiber, and by the color which comes out here, we suspected, voila, there must be something inside. Next slide. That's an overview how the fibers were found and prepared, and you see sometimes you have clear fibers, single fibers, isolated, that have sometimes which are together, which are nearly glued together. You can't see single or isolated fibers, but it gives you an idea how complex it is to prepare it, to understand what is inside, and how the people found it. They are very sensitive to everything. If you touch one with the hand, it nearly glues on your fingers.
I've experienced this. I'm sorry.
Yeah.
From personal experience. Now, can we go back though to that one slide upper right, 11C? I do see some black material in there. Is that just something different, or is that?
That may be that this sample was collected, let's say, from a place where any black thing was around.
Okay.
Maybe that's from a plant, maybe from the bottom. I don't know it.
Okay. All right. Thank you.
Next slide. Well, we're coming to scanning electron microscopy, and you see left. That's the instrument. I made all these pictures. What is the difference from scanning electron microscope to optical microscope? We shoot on the sample with an electron beam, and the electron beam pushes some electrons out. They were backscattered. We call that backscattered, and then you get the picture. And the picture is modified, or let's say is used together with the software to generate a picture of your sample. Okay. Mm-hmm. Next slide. These are now pictures taken from the scanning electron microscope. You see as well sometimes fibers, single fibers, really resolved, and other which are more or less together. And the two on the bottom show you one let's say one fiber accumulation where we have already material on it. Maybe it's crystallized out of the fibers, or it's even take off from the bottom or from the place where it was collected.
Wow. This
is once again a picture. The magnification is on the right side already 200 times. And there the picture on the right side is interesting because what we believe that the electrospinning process, which is behind to produce such fibers, is not completely successful. You see it's glued together, but the fibers come anyway out of this black, of this white part, and they are not single or not isolated. So maybe technique is not complete, or even this was built during they spread it off from the airplane due to the hot jet gases, that it was melted again. Yes, was melted together or melted again.
Yep.
So there might be, so what we're seeing then is many times what we identify out in the open here in California, in the US, are these webs, and they're clumped together. So that might be the ones that have been melted that make it easy for us to identify, whereas the ones that were more successful weren't exposed to heat, didn't clump together, and are just fine little strings just falling from the sky, you know, somewhat unnoticed. So this is probably why we see these weird clumps here and there, is because they got exposed to high heats and makes it very visible for our naked eye. Is that correct?
Yeah, maybe if they are really spread out from airplanes with jets, you have a hot stream behind the jets itself, and this may be modify the fibers. I don't know it. We have more than enough fibers which are single fibers, but we have also some which are glued together.
Okay.
And this is another technique where we can prove, together with the so-called energy dispersive X-ray, it's an X-ray method, that we have in fibers overall. We have, again, carbon, nitrogen, even oxygen, and the two elements which are outstanding a little bit, aluminum and sulfur. But we have 2 times proven that the elements, once with the inductively coupled mass spectrometry, plasma mass spectrometry, and with the energy dispersive X-ray spectroscopy, that these elements are really in the fibers and have any function there. Mm. Next slide. Well, that's now the key investigation we did. As I said before, we had great problems to get really a clear and a planar cross-section cut with the microscope device. And here we had success. We did a prism, and the prism was as long, cut it with small, very thin slices, till we reached a place where the fibers were clear cut, and we saw the inner diameter, the inner opening. And you see on the left-hand side where the red marker pen is, there we have measured this was one trial or one sample we took, and there on the right side there's a black marker pen. This was the second observation we did with the scanning electron microscope. Next slide. And these are the first pictures you see where we have really successful cut it. You see all the fibers are open. You see they are hollow inside.
That is staggering. That is a
Yeah.
staggering. image.
And the next you see, Christian is with the cursor exactly there. The material was inside was slightly pulled out through the cutting process. That's why it's like a tongue. So came the material inside out.
Right there.
Yeah.
And were you able to analyze the material inside these specific threads?
Yeah, we
Yeah.
did the solvent extraction. That what we later did.
We're getting to it.
Okay.
Mind-blowing.
We're just, going the whole step so everybody can really see how deep this actually went. So we're getting to the meat.
Yeah.
Okay, ready to the next?
Yeah, right. Wait, please. Right side, you see, even we have fibers with an inner diameter which is below 1 micrometer. It's roughly 900 nanometers. So they have a finishing process where they can vary the outer and the inner diameter. Maybe it's a normal process, but they can vary it, and they can, with this way, they can they can decide how strong is the loading. If you have a greater inner diameter, you can more load, and if every fiber is loaded, you have a completely higher quantity which you bring down. Understood?
Oh no, I'm just blown away. I'm also I'm also thinking about how this is almost like a time release. So these come down in these webs. You're not being exposed to it right away unless perhaps it's raining or there's moisture outside or you're inhaling it, and then it slowly dissolves and is released. And it's fascinating that this is the vehicle that they want to release these compounds through. It's fascinating, the thinking behind that. Like, why are they doing that rather than just spraying it out loosely and letting it, spread. So
Wait till you hear about the patents, Renette. It's going to blow your mind.
And what you're anyway right. What they know is that they can make a controlled release.
Yeah.
Because if we don't know exactly how long it takes to dissolve these fibers, the material outside fibers, to get the inner part on the ground, for example, we don't
In
know
the
it.
environment, yeah, exactly.
Yeah, it's not clear. It can be very shortly, or can be supported by rain, or maybe by any type of weather. We don't know it. And you see, that's another preparation we did. We have quite a lot of fibers, and once in the middle on the left picture, you see it's cut it along the whole fiber, and you see the whole place inside. You see the whole space.
Right here.
Yeah, that's
Right.
it. Yeah.
So that's where the payload is inside of there.
Yeah.
We can see when they cut it, it went lengthwise, not across, lengthwise. And you can see this, like, that tube is wide open. So that's why we can see right inside. Right.
Oh, so this is essentially what we're looking at is you spliced it down and you cut it open.
It opens, yeah.
Laid it.
Yeah.
So now we're actually seeing in, rather than the cross section, we're seeing in long ways.
Now,
into
when here on the right, it will tell you now here, this on the right is now a clear cut across.
Yeah, it's a clear cut, and there you can see there must be something inside as well. Huh? Not only the tongues which come out of the fibers, you see directly, you see now inside. Huh? Next slide, please.
Renette, it almost looks like a sliced okra, right?
That's exactly what I was thinking. It does look like an okra.
Yeah.
And none of this is living substance, right? None of this is living whatsoever, correct?
No, we cannot identify the substance by scanning electron microscope. We can maybe decide if it is aluminum or if it is nitrogen, but we could not say what the molecule is, the substance itself, which is in molecules. We will see it later. And if we go back to the picture now with a 6,000 times magnification, we clearly see there's inside material. It's inside material.
There you have.
The inner diameter is something about 3.2 micrometers, and the outer diameter of the fiber is something like 4.8 micrometers.
Yep.
Who dreams up this stuff?
All right. Now we're coming to the real fun part too. Philip is going to tell us about the patent.
Oh, okay.
Well, so yes, what I would highlight too, of course, I did extensive patent research, but what really struck us most is this patent family with the European granted patent 1755382. This has a priority date of May 2004. It was first filed in Germany as a German patent, and this specific one was granted in 2013. And it's quite a patent family. There are also US patents. I just I noted them as well. You can see on the first line within the white spot of the slide, US 8017061 and 8431064, which are more or less the same with some varieties. And just so as to recap the highlights out of the claims of this patent, it describes a method for the application of nanoscaled polymer, or as Hans-Jörg mentioned earlier, polylactides, which are the educts for these materials. And these are fibers or tubes or hollow fibers, and they are used as carriers for agriculture or otherwise applicable active agents. And the application is used using electrospinning, specifically from airplanes or drones, but it can also be done from machines like trackers on a field. And the most interesting part is the polarity of the jet where this material is spun out, and the land where it shall go to is used as counter electrode. So the electrical polarity of the jet, of the nozzle, is opposite to what is expected from the land where it shall go. And there are different methods as to how this active agent can be blended or just built inside of these electrospun hollow tubes or fibers. And there can be several stages so that there can actually even be multiple layers of different hollow fibers within each other, so that different agents with different release times can be brought together in one single fiber.
Can you, the very beginning of what you were talking about, can you explain that to me like I'm a second grader, like in layman terms, exactly what were you talking about, the polarity and so on? What does that mean to us?
So there is a hollow nozzle, and this specific polymer, as Hans-Jörg has elaborated, that is nothing that is known from the commercially available polymers, can be taken in a plane or in whatever kind of machine as a liquid. And this nozzle has predominantly a positive charge, a positive potential. And then this is spun out, so thrown out like a jet from this nozzle. And the fiber develops using the ground as a counter electrode. So you need a field of a positive and a negative charge. And within this electrical field, this polymer, this liquid polymer, is then polymerized into a fiber, into a fixed fiber that is not liquid anymore, and is then going to the target area of this negatively charged ground.
So so it's more than likely whatever vehicle, vessel, it's liquid form, uses the earth, once it spins it out, it creates the actual strings itself, and is released. So it's not, the strings aren't being released. Mm-hmm. It's coming out liquid form, and with that type of polarity, it produces these strings.
Exactly.
Philip is going to expand on that patent in the next slide.
Right. So electrospinning is a technical term that is used in a variety of industries for producing fibers, hollow fibers or also non-hollow fibers. But with this patent, they have shown that they can even use this on a huge distance between the electrode from which the material is shot out through the nozzle and the counter electrode, which can be somewhere in nature. And then the fiber generates within this distance between the jet's nozzle and the counter electrode, which is the ground. And what was
there's a likelihood when this is being released, it's being released and becomes like one long chain of fiber, and once released, it kind of breaks up into small little pieces and disperses. Is that correct?
Exactly.
Wow.
So in a very naive way, you can think of maybe, I don't know, in the 80s there were spinning devices, mechanical spinning devices that did actually knitting. You could do knitting of a tube, which was of course macroscopic. So it came out from a single fiber, and then you had a hollow tube, which was purely mechanic. But this is in a nanoscale, and of course with the electrical field, a similar way of producing a fiber out of a liquid original material. And you can and as they describe in this patent, you can have different tanks with different materials, and then spin one of these fibers inside the next one and even the next one, so you can have multiple layers of different materials, one inside the other. And they also describe that they have really nanoscales. They have shown down to 10 nanometers diameter, up to 6, and they even mention 50 micrometers. So it's exactly the range of dimensions that we also have seen with these microscopic samples.
Christian, any of you remember about 15, 20 years ago, there had been a scientific announcement where they had been able to mix, this is so bizarre, never made sense to me back then. They were able to take spider silk, spider webs, introduce it into goats, and the goat milk actually produced this synthetic type of spider web through goat milk. Any of you remember that?
I heard a different story. But anyway, I don't want to take away time here, but I learned about HIV serums that were put into goats, and then, because of their immune system and all that stuff, they used it through goats and create that serum and stuff. But that what you're talking about, I did not hear. But maybe, Philip, why don't we go to maybe the next slide for you, because you're going to bring the real crazy news, Renette. You're seated, right?
Unfortunately, yes. Yes, I might need Velcro so I don't fall over. Yes.
Maybe just quickly to your question. I do remember that. So like 15 years ago, as you say, there were many different scientific research projects that tried to fabricate artificially spider silk, because spider silk was recognized as a very stable and very interesting material. I don't remember specifically goats, but I do know that there were several experiments using genetic editing, so to say, as to artificially produce spider silk. So and I do think that
the genesis to this is what it seems like to me.
Yeah, really, exactly. One remark. What we need besides the, let's say, solution of the polymer in a tank, wherever it is, maybe an airplane, maybe on a tractor, we need the material what we found later on, what is inside, is mixed in the same solution, I believe, isn't it? So that during the spinning process, the whole fiber is filled at the same time where they spun out with the material that we found later. Right?
So it spins out the fibrous material that's hollow, separates out the actual what's in the payload all at once.
Yeah, all in one top.
Unbelievable.
Good. Philip, you want to go on?
That's also, but maybe if you can quickly go back to the former slide, you can see at the very end that these materials, so actually the fibers themselves, are biodegradable. So that is really meant, that's also elaborated in the description, it's meant as to slowly over a certain period of time get rid of the payload. So really to deliver the payload to wherever it is.
Release, yeah.
But it's like a time release. It's like a time release.
Exactly.
Yeah.
So now you can go to the next one, and this is still the same patent, continuing claims. So of course, just some highlights out of claims. Oops, sorry, I got a visitor here. Sorry. There, what is really surprising, they even write it themselves, surprisingly, it was successful so as to use very specific parts of plants or even animals to be used as counter-electrodes, to really specifically deliver these fibers to these specific places, like limbs, hands, feet, arms, legs of animals, humans, or specific parts of plants, wherever exactly they wanted it to be. So they measured the electrical potential of the target area and then fitted the electrical potential of the first electrode on the nozzle so that these fibers really stick to these specific areas where they want to have them delivered.
So they can specifically target where these fibers are essentially going to land.
Renette, if they decide to go after the potato fields in Idaho, there's no longer Idaho potato, they can destroy the potato fields.
Well, they can target individuals.
Yes.
Yeah.
That's why I ask you if you're seated, Renette, because people are going to listen to this. This is crazy. That's why we need the new administration needs to help us here with lab work and get behind us.
Next level. Okay, this is unbelievable.
Yeah.
So, and Philip, what you mentioned last time, the patent is 2005, and we have now 2045.
Exactly, and this patent specifically speaks of regional actions for release. So we are convinced that the people behind this patent, or at least this specific patent, is not really what is behind what we have seen and where we got all these samples from, because these samples, they have been distributed much more than regionally. So there must be a continuation of this technology, but we are quite convinced that this must have been the origin of this research. And as you can imagine, some really specific research will never get patented, because, or at least if it gets patented, the patents never get published because it's considered a national secret or whatsoever. So we are convinced that this patent is really just a very small beginning of the technology. It just shows that this technology existed 50 or 20 years ago already, or more than 20 years ago.
Yeah. So you can imagine, Renette, we're talking about agriculture use, but obviously if agriculture has it, the military has it before.
Christian, are you finding any correlation with NATO nations? Like, for instance, we do see that the planes that are geoengineering, generally they're somehow connected with NATO, they're NATO nations. Are you seeing this as well? Is there any connection with NATO and these patents or their application or distribution at all?
I think it must be. And we have some ideas. We have other research that's running behind the scenes. We also have kerosene things that we have looked at in labs from different airports. It's really tough to get kerosene samples, and so we have different activities in the background which are confidential. I don't want to talk about it right now in that specific conference. Yep.
I understand.
Yeah, so, Philip?
So, as a last slide in the whole patent world, we really wanted to limit this to some very specifics. This is an older patent which has been referenced in the patent, as I have explained before. And the reason why I wanted this one to be included in the slides is that you can see these are really the official patent figures on the right side. So you can see first a drawing, a schematic representation of such an electrospinning apparatus. Here you can see the two electrodes, the one on the nozzle, which is positively charged, and then the ground, which is negatively charged. And on the right side, you can see microscopic photographs, which look identical to the ones that Hans-Jörg was able to obtain in the lab. So you can exactly see these hollow fibers and the microtomes, which show the orifices for the specific payload.
Excellent, excellent. So we're good. Thank you. We're going to go on here. Back to Hans-Jörg. Yep. Thank you very much, Philip. That was excellent.
Philip, that was extraordinary. And all of you, your research, it has to be highly, highly commended. This is unbelievable. You are doing such a service to humanity exposing this.
Okay, we applied another method to prove that the origin of the polymer system is not let's say, synthetic or technical one. It must be another one, and therefore we use this pyrolysis gas chromatography. You see the scheme in the middle. You have a pyrolysis unit which heats the sample, mostly polymers, very quickly up to temperature around 600 degrees, and then the polymer is cracked down in its adducts, monomers mostly, and then it's separated by the column chromatographically, and then it's introduced in a mass spectrometer where we can again say what the mass is and can make conclusions. Is it a fragment of the polymer? Is it a monomer itself, or is it a bigger molecule? Whatever comes out. Next slide. This is exactly now what we did with the thread 347, and you may keep in mind the pattern. You see you've got a lot of peaks, a lot of substances which are on a more or less regular basis, one after the other. And now switch directly, Chris, please, to the next slide. Here we used a standard technical nylon 6, polyamide 6, and you see clearly the difference. The main peak exists only of caprolactane. This is adduct which is used to produce polyamide 6. We only worldwide is used caprolactone. That's the mostly used synthesis to get polyamide 6. And you see the difference had nothing to do with our polymer, with our polymer from the fibers. Gives a completely different pattern. You don't have a main peak in the other one in the thread 347. You have a lot of peaks which come maybe partially from the inner hollow part, which is filled with any material. And this one, if you use as a reference the polyamide 6, you only get caprolactone. So we have two proofs that it's not the synthetic material, our polymer, which is used to spread around. It must be something else, and we clearly know that it's an amino acid composition.
Okay, so it's something different, but we don't know what it is.
We don't know. We assume that there may be 3 to 4 amino acids used. Okay. We don't have them detailed, but we know it's amino acids, and it's not a technical polyamide. That's clear. And amino acids naturally are foreseen to be destroyed very quickly compared, for example, with technical polymers. Technical polymers like polyethylene terephthalate needs 80 years roughly to be destroyed completely. But amino acid is destroyed in let's say in a few days. It depends on the weather, it depends on the ground, it depends on everything. Right. You see the difference.
So it's much, much harder to detect, Renette. They're really smart, you know? Yeah. So in other words, when our chicken or the pigs or the cows eat that from the field, it gets absorbed into their bodies and their bloodstream and their milk and on and on.
Well, this is how clandestine and deceptive it is that it's one thing to see some kind of spraying going on, and then let's say within 24 or 48 hours, everybody gets sick. Whereas this payload is delivered, it lands, maybe nothing happens until the first rain, or there's enough moisture in the air, whatever, and you cannot correlate when it was distributed and how it was distributed, because it just landed, and a week later, a month later, then it's released.
You got it, Renette. You got it.
Yeah.
Yeah.
Now we are at that part where we analyzed the extraction of the fibers. That is called fiber extract. And you see what we got with GCMS coupled. We got more than 50 substances out. And I focused later on only on a few important ones where I'm sure that the spectrum of the reference spectrum is identical to what we found in our sample. Next slide. That's the first one that you see on the top. On the top you see the gray field is what we found as our sample, and the spectrum below is that what we took from the NIST. NIST means National Institute of Standards, which is in the US. And I believe every registered substances worldwide is registered there. In terms of they have information about the analytical side, that means infrared spectroscopy, they have mass spectroscopies, you have NMR, nuclear magnetic resonance spectroscopy there, they have all the data, the physical data, what is the boiling point, etc. Everything is registered there.
So in other words, this is now substances that have been figured out to be inside those nanotubes.
Yeah.
And I'm seeing all the precautionary statements that come from it.
Yeah. Crazy.
And
So
it doesn't matter. We go ahead because everything is built up the same manner. On top, always the spectrum, the mass spectrum we got from the extraction.
Yeah.
And below is always the reference spectrum. And you see it fits very good. And this one is very critical. This is an epoxy derivative. And epoxy is a highly active substance, very dangerous sometimes. It depends where it goes. Therefore, you see the rhombus is left on top is irritating for skin and is irritating is destroying any surface, any organic or inorganic material. And you see, if you look down to the danger, to the precautions, toxic if swallowed, toxic in contact with skin, causes severe skin burns and eye damages, may cause an allergic skin reaction, toxic if inhaled. You see, and then you have the precautions, what you have to do, wash immediately, go to the doctor, use this and that, call poison center and so on.
Well,
that's information from the safety data sheet about this substance.
And I think again about how you're saying how we've been led to believe that the clumps that we're seeing that we can easily identify are the ones exposed to high heat, whereas this is being made and spun out, broken into thousands, millions, billions of tiny little pieces, spread everywhere, and can be targeted. Yep.
So now we have a very interesting one for you here, Annette. Go ahead, Hans-Jörg.
Yeah, and this is one you see. This is a substance which fits very good. So the spectrum of the sample we got with extraction, and the reference sample fits. And what is interesting, there's nothing known about this, no data available. This is a substance which is not registered. We don't know how to handle it. We don't know about the danger. We don't have any hazard information. This is
it's required by U.S. and international law that you have to put this into this database. And what you're saying is the chemicals that you have discovered, there's no presence of it anywhere in any database around the planet.
That's why we need your
data sheet. We didn't find any registration. The number it's registered. We have a CAS number on the top, but the safety data are not available about this.
Well, what frightens me, I mean, there's many things that frighten me about this, but also I just think about how right now in the U.S. they're putting mRNA vaccines into everything, in our lettuce, in our meats, in everything. It's insane. They could easily put mRNA or any other kind of vaccine in this as well, and we would have absolutely no idea.
It works great. It works great for depopulation purposes.
Yeah.
Next
one. Yeah, here we know it. You see, we have a good fit with the reference spectra, but again, the product is registered maybe as a product, but no safety data available. Everything, no data available, no data available.
Gonna go on. We're gonna have to go on.
If we go further, you see all these substances we found out. And if you look at the pictogram, always the rhombus, here it's a little bit in the middle. It's a warning because it's very, you have to keep it away from heat, sparks and so on, because it may be flammable. Then you keep away from the ground, bond containers, take precaution measures against static discharge. It's very difficult to understand why such substances are always used. Again, we have the death head. You see, and we go through, you see quite a lot of here we don't have any data. This is a substance we don't have nothing.
This is scary. This is really scary here, Annette.
Scary. But I have to do one single remark. As we assume it comes out from an airplane which has jets and has high heat in the jet stream. Maybe if the nozzles where the electrospinning is done is very close, then maybe that some part of the kerosene which has not been burned in the jet inside is also involved in the fibers. Maybe they are together outside, combined together in the fiber itself, because they are, let's say, morphological wise, they are very open. The polymer is not it's not like a let's say like a plastic or like a metal tube, which is absolutely tight. This is more or less open. The polymer allows that other things can penetrate. It's the same way it can be penetrated to outside.
Well, also what I find disturbing about this is, unlike, let's say, military chaff, which is fiberglass coated aluminum, and they use that to cover things for radar, but also when they're doing cloud seeding, they'll put out chaff so they can actually see through like radar, they can see where the cloud seeding is moving, so they can see if it's over their target. There's no way to identify this stuff being released, right? There's no way to identify it like chaff. Oh, they just released it on such and such date. You can't, there's no way through radar to see this, is there? There's not enough real metal particulate matter to make it identifiable, is there?
The only way what we can say is, first of all, if there is, let's say, metal components inside, then maybe they are included in the polymer backbone as a, let's say, as a static part. For the organic material which is inside, I think they really know what they do inside, and they know how to handle it, maybe concerning the release or concerning the loading.
Gotcha.
Hans-Jörg, maybe a few words about this, then we're going to have to pace through the next following slides.
Yeah, well, we found an histamine derivative, and the histamine derivative is normally not in the jet stream of any airplane. It's clear, so it comes clearly out of these fibers, and was allowed inside. Must be. We don't know exactly the structure. We only know it's a derivative of histamine.
Yeah, and Renette, no spiders are passing the histamine around.
Well, it makes me wonder too. I don't know what's going on in Europe, but right now in the U.S., all across the U.S., actually beyond the U.S., Mexico, New Zealand, we have people who are so sick right now with intestinal issues that do not go away for weeks, with colds that do not go away for weeks.
We have the same here in Europe and Switzerland. So many people. Yeah.
People who
getting
don't get
sick long time and several times.
Several times over for weeks and weeks at a time. Can't shake it. We'll have it come back again, maybe a different type of symptoms, but people cannot get better. They cannot recover.
And we have numbers of pneumonias as never before. I have talked to several friends who are doctors, and they said they have never seen as many pneumonias as this winter.
Yeah.
We're seeing the respiratory thing here also with the frontliners. Same thing.
The result of the mRNA injection.
Oh.
Yeah.
Okay.
Not only. I know many people who suffer from pneumonia who are not vaccinated.
Yeah,
Okay.
yeah.
Well,
It's clear.
that's interesting.
It's clear. Everybody who's vaccinated produces exosomes. Exosomes are distributed by air, in rooms everywhere, with contact on the skin, with contact everything. For me, it's absolutely logical.
I think this is something to point out and have people really pay attention to, but I don't know if it's because my inner circle and the people I'm around for the most part, are not vaccinated, but we have noticed that those who are not vaccinated, and I don't have a lot of vaccinated friends these days, but we have noticed those who are not vaccinated are the ones falling ill the most, which I think is quite interesting.
Wow. Yeah. Yeah. Well, we are coming to the summary here. Renette, Hans-Jörg, do you want to cover the summary?
It's very short that we know that fibers does not consist of technical ones. They are natural amino acids or their derivatives, biodegradable. The average diameter, is 4 to 5 micrometers. We have internal cavities, which contains chemical substances, as we have just seen with the GCMS experiment after solvent extraction, and they are highly toxic, corrosive, hazardous, and anything. And that what Philip crystalled out is that the patent describes exactly applications which makes it possible that the fibers are filled with material, and there are medical or active ingredients of pesticides, biocides, everything can be loaded, and it can be targeted. That's the most surprising thing. Targeted to certain things like hands, feet, legs, human animals, special fields, potatoes, for example. Yeah, that's the truth.
This truly is, and I'm not overstating this, but this is such a national security issue. It's huge. And I don't know anybody who knows anything about this anywhere except for.
Yeah, I think I am so pleased that we had the kind of foresight and especially the network to help to get this done. And I mean, everything happens for a reason, Renette. And with the changeover in the administration in the United States, our coordination, our teamwork, and if you can help us push, some things over there, the whole world needs to know about this. We need to stop this. And this is definitely a military ops coordinated with secret service and This is just really nasty stuff. But here, maybe a few words, Renette, and then I have another slide for us here. But just to let you know, our nonprofit organization, we do different things here, but specifically now for this is that we have prepared our website such that we can share it. We can share, obviously the video that we're doing here. We can share the PowerPoint presentation. We are set up to share the patents really easily. We can share the stuff on social media. The stuff needs to go out worldwide. We have this slide. We have, this is mainly Hans-Jörg translated this. All three of us worked on it to get it translated from German into English. Our first move was all in German. We had to translate it for English, and now we can use it for worldwide use. So then what we say is listen, people, start local, organize yourself in groups, go to the town halls, get involved, okay? Ask questions and help, support whoever is helping us here. What I have not mentioned, Renette, okay, and for the viewers here is such an analysis done in a lab. If you had to go and get a lab to do this, it will cost no less than 150 to 250,000.
Right.
Okay, and obviously for us it took longer because we had to figure out certain methods in how to get these things cut, and so metal didn't work, so we had to go to a different diamond knife, and there's a whole story behind it. So, and then we demand the investigation. I may have to move this thing here out of the way so we can see it. So we demand the investigation. This is now what we are getting prepared for, Renette, here. We're going to give the government the opportunity here in Switzerland to actually listen to us. We're going to demand a meeting with our lab team, just like what we got here. Hans-Jörg, Philip, everybody here. And we want the government department that is responsible for the environment, together with the parliament, the security commissions that are involved. We want a meeting with those guys. We want to present them. We go from the point of view that they're not involved. They're not educated. They don't know this is happening. Most of these people are not in the know. There's just a very few that know about this. And we believe that the Swiss government is not fully informed about what's happening in the sky. So I think this is internationally coordinated. So we're going to give them the opportunity to hear us out and then really watch what they're willing to do. And if they're not going to support us, then we're going to file criminal charges.
Well, I think we should do the same thing here. We're doing something similar with geoengineering in general, and that's a petition for ruling with our agencies who are set to, they're designed to protect us, and we're not getting the protection or the monitoring or the testing or the standards. And so
Yep.
I think perhaps either together or separately, we need to do the same thing with this, specifically saying, while we have not tested these synthetic spiderwebs here in the U.S., we have definitely collected them. I believe we still have some that we've been storing, some of our, women who've collected them over, around California, but put on notice our agencies who should be protecting us. This is extraordinary. And also,
Renette,
yes.
they're not synthetic. They're organic.
Okay, that's right. That's correct. They're organic. That's right. They're organic.
That's the crazy
But
thing.
I guess I would say man-made. They're man-made.
Yeah, yes.
Right.
So you can see here in the slide for Einvir. So this is our domain name. Everybody worldwide can come and get everything. We have a WordPress website, so it can be easily translated to different foreign languages. So you guys can share, that with us together. And then, I'm not sure if you have some more specific questions, Renette. And other than that, we're really at the end. People ask, how can we support you guys? We always say, well, with more money, we can do more projects. This project deserves definitely legal action. And we need to coordinate those legal actions. They're never cheap or free, right? People don't do everything pro bono, especially people that have the know-how and experience and skills to help us. And so here, people can support us from anywhere in the world. And, if we don't do anything about it, all the millions in our bank account won't do us any good. So now we have to have people that have money to support such cause. They need to step up with us. We're risking our lives. My two colleagues here, Hans-Jörg and Philip, and myself, we're risking our lives investigating this. And I'm sure people understand this is very sensible work. And here is our contact information. When we get to the end of the PowerPoint presentation, I'm sure you will also list that in your show notes. I can tell you we are extremely excited for your support out of California, your network with the new administration. If Kennedy and team can help us here get this to the next level, we would absolutely appreciate it. Our donors, our members here of our nonprofit organization are looking forward for the coordination and to work with you together in the United States and everyone else in your network.
Well, Christian and Hans-Jörg and Philip, I want to say thank you so much for your extraordinary and exemplary work and research. This is extraordinary. And as you said, everyone's been looking at COVID for these last few years, and you actually went a completely different route, and you are way ahead of the game. and the curve by actually identifying this. And again, that this is essentially a type of payload for anything to be distributed. And I have to say too, I've been speaking to many of my friends talking about and colleagues talking about, why do we have biolabs everywhere? Why do we have biolabs in the Ukraine? Why are any biolabs in China, US, anywhere even allowed? We are told that it's for our protection, but really it's being used against us with our own tax dollars. And so I would guess that more than likely it was a biolab somewhere around the world that probably created this spider web. So I think we have to really start speaking to the need for public pressure to bring an end to all biolabs around the whole entire world, because it's only creating a great harm and threat to all of us and humanity.
Renette, you're absolutely correct, and I don't interrupt you. The problem we face here, all of us, is that our politicians don't look at this as a priority. They've never heard about it. They get a stack of this mail every day in their parties, in their fractions. No one talks about it, so it doesn't become a priority. When does it become a priority? Only if we, the people, the sovereigns, are taking it in our own hands. And that's what we're doing right now. We're going to start swarm intelligence and start really educating, our family members, our network, from all the way from those local communes to schools. We need to push from the bottom up, and all the people that have been voted, at the county level, at the state level, and at the national level, senator, congressmen, they need to be aware of this, because why, Renette? They're also eating the milk, or drinking the milk, or eating the meat. Or if their children are playing in the lawn and they think it's some kind of, maybe some sugar candy or something that fell out of the sky, and the kids eat that stuff, from the lawn, or their dogs, extremely toxic for dogs, we learned. So with the histamine in it, So, this deserves full attention, and it deserves major pressure to our, politicians and our government, apart from the communes, the state level, all the way up to the national level. So, these people are insane who are doing this stuff, they're nuts.
It's insane, and nothing's protected. And we talk about this with geoengineering in general. It doesn't matter if you're trying to protect the salmon or the redwoods or the children. Everything, including pollinators and aquatic life, are exposed to this, and there's no escaping this. There's no escaping this. It doesn't matter whether you're a political leader or just your common average citizen. We're all being exposed to this, and it's very clandestine. As I said, nobody knows about this. You are the first in the world who have actually uncovered this, and it is frightful for those of you out there in the US, Europe, anywhere around the world. If you do come across these spider webs, do not touch them with your bare hands. Use latex gloves. If you can, try to keep a sample, put it into a mason jar, put it in the freezer. Perhaps we can test it later when we have more access to the proper labs. But again, do not touch this. And in fact, if you do have it around your property, best to put the latex gloves on and try to remove it to protect yourself, your animals, your pets, your ranch animals, and other wildlife.
Maybe to expand, Renette, right there, jump right in. What we're prepping, just so you know what we're doing here, we're telling the people, get your own, accumulate those on your own, put them in the jar, label it, date, location, everything like that, and then go to the next. We're putting together a complaint, so to say, so we can go to the actual police station or the public prosecutor and actually file a claim, and you have the evidence right with you. And then along with that, also our lab analysis. So this is how we're getting thousands of people to start charge here in Europe. That's what our next step is. We do.
All right. Well, everybody, you have your action items and your marching orders. You find this, you know what to do, make the claim, collect it really with kid gloves. Do not touch this no matter what. Very clear. It's toxic and poisonous. And we are sounding the alarm. We're sounding the alarm worldwide.
Excellent.
Well, thank you, Christian. Thank you, gentlemen. Again, extraordinary work. I will be getting this out immediately with all the proper links and so on to direct everybody. And I will be spreading this everywhere I can. If you have social media, folks, if you're watching this on Substack or somewhere else, share this like wild, because this is a system that has been at play for quite some time, and we have been blind to it until now. And everyone needs to know it's truly, this is a cautionary tale for all of us, what's going on.
Thank you so much for having us. Thank you, Philip and Hans-Jörg. Thank you very much for your time.
Thank you, gentlemen.
Thank you all. Bye-bye. Next time. See you.
Thank you.
Bye.
Arms of Love mission by Limitless Ministries is supported by a Canadian Christian woman. Originally from Kyrgyzstan, their Women's Crisis Center helps vulnerable mothers and children escape trafficking, abuse, and poverty, and teaches them skills to enter the workforce. Consider donating to this excellent mission. armsoflovekg.com